Hi, welcome to this webinar on camera-based non-contact health sensing. My name is Daniel McDuff and I'm a principal researcher at Microsoft Research. I'll be presenting the first half of the webinar, and then I'll be joined by Xin Liu from the University of Washington, who will be presenting the second part, which will be focusing on our latest work to appear at Europe's 2020. During the webinar, you can ask questions through the text Q&A widget on the website, and we will be answering those questions live through the text chat. Following the presentation, we will be doing voice Q&A live where you can ask questions in person, and we can explain any answers in more detail. So let me introduce the topic of this presentation, first by framing it in very relevant real-world events. We are seeing, due to the COVID-19 pandemic, that healthcare is transforming. One of the most obvious ways this is happening is a transition from in-person care to telehealth. And there's a couple of reasons for this. Telehealth has advantages as it enables us to protect healthcare providers and patients. It also helps reduce travel time and expenditure, means that people need to take less time off work. They don't need to find childcare for their children. And so it's in many ways preferable. Many people have considered already using telehealth, or many of you may have already used telehealth services during the pandemic. And this is something that's likely to continue even into the future, because these advantages, the cost savings and the protection of both patients and providers, is something that will be a continued benefit. However, some people have concerns over how well their condition can be diagnosed or treated when their only interaction with a healthcare provider is over a telehealth platform. One of the reasons for this is it's often very difficult to objectively measure the state of a patient. And what I'll be talking about, camera-based physiological measurement, can potentially be used as a way of gathering these types of measurements. Around the world, telehealth is becoming more attractive and used at increasing rates. And one of the reasons for this is because it can improve the efficiency of healthcare by allowing providers to see more patients more easily. In addition to that, it can actually allow access to patients who need specialists for their care, but maybe live in remote locations or places where there isn't many specialists available. One example of this is cardiology, where telehealth has actually been utilized to a larger degree than many areas of healthcare. Cardiology relies on specialists who are able to analyze the cardiac signals of patients, and in many cases there may not be a cardiologist that you can easily reach, and so telehealth has advantages to improving access to care as well as in efficiency and cost savings associated with that. In addition to telehealth, camera-based non-contact measurement could be applied in many other domains. Baby monitoring or monitoring of infants in the intensive care unit in a hospital allow us to measure the state of an infant without having to place sticky, uncomfortable electrodes onto their bodies. In some cases, babies can even get infections from these electrodes, and so having a camera-based non-contact measurement technique could really improve the quality of care. In elder care, cameras could provide access to measurement for people who may be not able to travel easily to a surgery or a healthcare provider, and enable more easy and higher quality telehealth visits. In chronic disease management and global healthcare, we could allow people to measure physiological information more easily, more scalably, without having to rely on expensive and often hard to obtain devices. So let me start by just introducing the optical basis for these methods, where we're measuring the physiological signals from videos. Camera-based measurement relies on capturing subtle changes in light reflected from the body, which is modulated by both pulsatile information, or blood flow, and respiratory information, or breathing in and out. As light hits the body, some of it's absorbed and some of it's reflected and picked up by the camera. And the amount that's absorbed depends on these physiological processes. So as the blood flow in the skin changes, it changes the amount of light that's absorbed or reflected from the skin. And the same as we breathe in and out, it changes the incident light and the amount of light that is captured by the camera. So we can actually use this principle in order to extract the physiological information from a simple webcam video. How this works is using an optical technique, and I'm going to use Schaeffer's dichromatic reflection model as a basis for grounding our computational approaches. In the DRM, C here, which you see on the left of the top equation, is the RGB color signals captured by the camera, which is a function of the luminance intensity, or the brightness of the light in the environment, and the specular and diffuse reflections from the body. These specular and diffuse reflections are changing over time, in part due to motion or lighting changes or other things. But the diffuse reflection is changing mostly based on the underlying physiological processes, the absorption of light due to the volume of blood in the surface of the skin, or the volume of the body during the increase or decrease of the respiration motion. We have a final component with this, which is the quantization error, which captures the camera noise, essentially. When we substitute in the three equations at the bottom into our DRM equation, we end up with essentially a mathematical model which relates these physiological processes, which are varying over time. You see P of t highlighted in red, and the observed camera signals C of t. We can simplify these equations a little bit by making assumptions about small components which can be more or less ignored, giving us a final representation. And what's interesting is that P of t, the physiological processes, are actually a complex combination of both blood flow and respiration information. So you'll see in the final equation that P of t is replaced by B of t and R of t, representing breathing and pulse information. The reason this is true is the principle of respiratory sinus arrhythmia, where we observe that heart and lung function are actually correlated, and there's shared information in the pulse and respiration signals. With RSA, the interbeat intervals of the heart are actually synchronized with our breathing in and out. And this correlation between these physiological processes is useful when we are looking at modeling them computationally. And we'll actually see later on, when Xin presents our latest work, what we do is treat this as a multitask learning problem, where we want to recover both the respiration and pulse information at the same time. So now let's talk about some of the computational techniques that are used for recovering physiological information from videos. What you'll see on the left-hand side here is a video recorded of 3 people. And in this case, we're extracting a region of interest for each individual around their face. And there's a couple of reasons for choosing the face here. One is faces are relatively easy to detect. And two, the skin is exposed often. So they provide a good way of measuring pulsatile information from the skin. We can't do this optical measurement of pulse signals through clothing, for instance. So we need to be able to see the skin in the video. So for each region of interest, what we do is separate the three color channels captured by the camera. So that's red, green, and blue. And then for each frame of video, we do a spatial average of those pixel channel information. And the reason we do a spatial average here is because each pixel is essentially a noisy sensor. Each pixel captures a bit of information about the physiological change, but also a lot of noise due to the camera quantization, as well as other variations happening in the video, such as head motions. And it's been well established that camera quantization error in particular can be significantly reduced if we average together multiple pixels. So when we average these pixels for each channel and for each frame, we end up with three time-varying signals: a red signal, a green signal, and a blue signal. These signals each capture some information about the physiological processes, whether that's pulse or heart rate or respiration. But they also each capture noise. And each channel, because of their different frequency sensitivity, captures different proportions of these, the signal and the noise. And so this sets us up for a very traditional signal separation problem. We want to find the underlying signal of interest, which in this case, I'm going to use the pulse signal or the heart rate signal as an example. And we want to separate that from sources of noise due to motion or lighting changes, etc. So that signal separation here is the main component for many of the early approaches for doing camera-based physiological measurement. One example of this is independent component analysis. Independent component analysis involves using assumptions such as the periodicity or non-Gaussianity of the physiological signal in order to extract that information from the observed red, green, and blue color channel signals. There have been subsequent improvements over these methods. One example using a chromium-based approach, and another using a plane orthogonal to the skin mapping. In both cases, these advancements leverage more information about the optical and physiological properties of the body in order to improve how we demix the physiological signals from the distractors or the noise. However, as with many domains of computer vision or applications of computer vision and machine learning, simple signal processing techniques often don't fully capture the complexity of the spatial and temporal variations that we're observing in these videos. So neural approaches provide a nice mechanism for learning more complex representations of what's happening. One of the first neural models for approaching camera-based physiological measurement uses the following approach. So we take our input video, that you see on the left, and we have two different networks. The first of these networks you'll see highlighted in green is the appearance model. The input to this network is the frame at time t. And what this network is there for is in order to guide a second network, which you'll see highlighted in black, which is the motion model. And the motion model has an input which is the normalized difference of subsequent frames. So the normalized difference between frame at t plus 1 compared to the frame at time t. This motion representation you'll see is essentially just a set of pixels which reflect the change in light from frame to frame picked up by the camera, and doesn't have a lot of the information about the skin color or other information that we might normally use to segment the region of interest in the video frame. And that's why the appearance model is there, to help guide which regions of the motion model we want to focus on in order to extract our physiological signal. So each of these networks has a fairly standard convolutional network set of layers, followed by a fully connected layer. And the goal here is to predict the pulse signal value at time t or t+1 based on the input couple of frames. So the input to this model is just 2 frames, and the output is a single prediction of the current pulse signal value. And then we run it across all of the frames in the video to get the output pulse waveform. A nice component of this model is the attention mechanism that connects the appearance and motion branches. What this does is essentially segment the regions of the video that contain strong pulsatile or respiration information. And to most intents and purposes, that's skin segmentation, because the skin has the strongest, typically the strongest pulsatile information. But also the strength of that signal varies across the face. And so the attention mechanism is actually able to learn some of those variations. What you'll see on this slide is some examples of videos highlighting the regions that the algorithm focuses on in order to extract the pulse information from the video. You'll see that the yellow regions, which reflect high signal information, are in the forehead and on the cheeks, whereas the hair, for instance, or the clothing is dark blue, which reflect that there's very little pulse information present. You also notice that regions that have heavy shadow, for instance, around the eyes or below the nose, also have a darker blue, reflecting that generally regions with brighter luminance tend to have a stronger signal that we can leverage to extract the pulse information. Another nice thing about these neural models is that we can actually do magnification of these signals as well. So to help illustrate what we're measuring here, on the left-hand side, you'll see a video where we've magnified the pulse information, and you can see this color change. In particular, look at the forehead, where it's easiest to see the pulsation or the red color change in the skin. And that's what the camera is picking up, but it's been magnified several times to help you see it. On the right-hand side, you'll see an example where we're magnifying the respiration information. Look in particular at the shoulders of the individual as they move up and down as they breathe in and out. And if you pay particularly close attention, you can even see the nostrils flare in and out as the individual breathes. Again, these motions can be recovered by the camera, and we've magnified them here to make them easier to see. But generally speaking, they're very subtle signals, which is why we need to use computational techniques to extract them and boost the signal-to-noise ratio. We have a couple of resources that might be useful if you are interested in investigating some of the techniques for doing camera-based physiological measurement. The first is the IPBG Toolbox, which is MATLAB implementations of some of the unsupervised signal processing techniques that are used for extracting pulse information from videos. And also we've got a repo including our latest deep neural network code, which will be presented at NeurIPS. The paper will be presented at NeurIPS 2020, which is a multitask, efficient convolutional attention architecture for doing both pulse and respiration measurement from videos. And I'm going to pass over to Xin, who's going to walk you through that approach and show more examples of the types of physiological signals we can extract from these videos, giving some demonstrations of the types of signal-to-noise quality we can get, even in the presence of, in some cases, large head motions and other variations within the videos.
Hello, my name is Xin. I will be presenting the second part of this webinar. Today's topics will be about the multitask temporal shift attention networks for on-device contactless vital measurements. This is a paper accepted by NeurIPS 2020, and it's a collaboration with Josh Front, AutoML, and Shraddha Patel, UW, and Danny McDuff. I will start from the challenges on this project, why we start this project. The first one is camera-based cardiopulmonary measurement is a highly privacy-sensitive application. The data are personally identifiable. So those data are the videos of a patient's face with sensitive physiological signals. And therefore, streaming those data or uploading any of those data to the clouds to perform analysis or inferences is not ideal. So keeping all the data in local also avoid tons of regulatory issues. The healthcare community and the machine learning community are all pushing towards to this direction. The second one is this application requires ultra fast speed to run on device. People might curious why. Because the contact sensor usually run at least 100 hertz or 256 hertz. And if we want to make sure that happens on device, we have to make sure our model could run around 250 FPS to 100 FPS. This is not normal in on-device machine learning because on-device object recognition or any other computer vision task, they usually require 30 FPS and 60 FPS, and they can claim a real time. But in our case, we do require ultra fast, at least 100 FPS. And also, if we can run our model on device for at least 100 FPS, we can capture the heart rate variability. Heart rate variability is a key metric in a lot of physiological measurement, as well as some mental health is correlated with your stress level. So HRV is a physiological phenomenon of variations in the time interval between the consecutive heartbeats in milliseconds. So in order to measure those variations in the milliseconds level, we do have to make sure our model runs super fast on some constrained device. And also if we can make this algorithm run on device, we can also enable some very amazing optimistic sensings. For example, if you look at your phone and the phone camera can record your face while unlocking the phone and also measure your vital signals. Moreover, cameras can offer a scalable measurement. Imagine that in the fitness centers or in some elderly service, you can just use the camera to remotely measure everything. You can really scale up the physiological measurement, especially during the COVID. I think this is really important. And our solution for that is we call it Multitask Temporal Shift Attention Network, MTTS-CAN. So MTTS-CAN has a few features. I will start from the first one. So the first one, we efficiently learn the spatial features that maps from the raw RGB values to latent representations corresponding to the pulse and the respiratory signals. However, this probably was not enough because there are tons of temporal noise causing the neural network harder to learn the spatial information and the physiological signals. So we also learned those temporal features to offset various noise, such as head motions, ambient illumination, and changes. For example, if I'm shaking my hands, the light, those illumination changes. So this could cause a significant difference in physiological signals on your blood. So this is something that's really important compared to the 2D CAM, which can only learn the 2D spatial maps. We want to learn both spatial and temporal informations. The second one is our network can learn relationship between the cardio and respiratory systems. So we leveraged a fact called respiratory sinus arrhythmia that Daniel talked in the first part, where the lung and heart functions are correlated, and therefore there's a shared information in the pulse, PBG or ECG, and respiration signals. And the third one, our system could work in the real time to support various telemedicine deployments. For example, it could work on your cell phone, it could work on other mobile devices or on your computers. So I will start a little bit background about what is the temporal shift module, because this is a key component in our MTTS network. So the rationale behind of temporal shift module is very simple. So the motivation behind of that is how could we do something special to enable temporal information exchange without adding too much computational overhead, right? So, the TSM performs tensor shifting before the tensor is fed into the convolutional layer, as visualized in the figure. So there are two parts of figures in the slides. The figure A is the original tensor without shifting. This is basically original tensor, but it has a 4D dimensions. It has 4 dimensions. The y-axis is temporal dimension. The x-axis is the channel dimension. So the TSM first splits the input tensor into 3 chunks across the channel dimensions. I have to emphasize that for the illustration, the figure B shown here, it doesn't split into 3 chunks. It splits the first channel as one chunk, and the second channel as the second chunk, and the rest of it as the third chunk. But in reality, we split this evenly into 3 chunks. For example, if your input tensor is has 9 channels, we split the first chunk, which has 3 channels, and the second chunk has second 3 channels, and the third chunk has the third 3 channels. So after splitting the original tensor into 3 chunks, then it shifts the first chunk to the left by 1 place, advancing time by 1 frame, and then shift the second chunk to the right by 1 frame, delaying the time by 1 frame. So as the figure B illustrates, it moved the tensor on the first channel down by 1 place and add a 0 padding in the beginning. And the second chunk, it moved the tensor up to by 1 place and add a padding 0 at the end. So, and both shifting operations are along the temporal axis so that it can help the temporal information get exchanged. And both the shifting operations are along the temporal axis. I just want to emphasize that. And the third chunk remained unchanged, as shown in the figure B. The third channel and to the last channel remain unchanged. And this is worth noting that tensor shifting does not add any additional parameters to the network as I described. It basically is shifting the tensor before it fed into the convolutional neural network, but enabling information exchange among the neighboring frameworks. So this is the architecture figure about our proposed network. We call it Multitask Temporal Shift Attention Network, MTTS-CAN. MTTS-CAN has 2 branches, motion branch and appearance branch. I will start from the appearance branch. The appearance branch is the raw RGB value as we showed it here. And the input size of the appearance branch is 1 by 3 by 36 by 36. And it has 4 convolutional to these operations and 1 average pooling operations. And in the second comp to the operations and the fourth comp to the operations, it generates 2 attention masks for the motion branch. So in the motion branch, we took the normalized frame within 2 consecutive frames. So you will see the normalized frames looks a little bit different from the regular appearance frame because it's normalized frame, and we add a TSM tensor shifting module on the convolutional 2Ds in the motion branch. And it's worth noting that in order to best optimize the latency in MTTS scan, we only compute the appearance branch by once, and they generate a attention mask for n frames in the motion branch. For example, if my batch size is 20, the motion branch takes 20 by 3 by 36 by 36 as the inputs. It has 20 frames as inputs. And however, in the appearance branch, we average those 20 frames to a single frame and provide an average attention masks to all those motion frames in the motion branch. Why are we doing this? Because the RGB values do not change that much, especially within a short period of time, such as 20 frames or 10 frames, so that we can save a lot of computational power in the appearance branch. If we compute the appearance branch by 20 times, you will use 20 times 4 convolutional 2Ds. So it's a huge amount of resource. So, but in our case, we have an average frame and only outputs attention mask by once. Okay, so after we got some outputs from the motion branch, we have 2 different branches for the fully connected layer. One fully connected layer is outputting the respiration signal. The other one is outputting for respiration waveforms. And people might be also wondering why attention mask is important here, right? So because after the tensor shifting module, there's some extra noise showed in the figure below the architecture figure. So you can see before the TSM, you can briefly see a human face, but after TSM, there's some extra noise due to the tensor shifting. So by applying this attention mask, you can help this network to learn much better and focus on the regions that contains signals, biosignals. People might be also curious, is there any other ways to perform spatial temporal modeling? And the answer is yes. 3D CNN is actually well known for this spatial temporal modelings, right? Because it takes a 4D tensor as inputs, and you can learn temporal relationship within multiple frames. So we also propose a 3D CAN based on the existing state-of-art 2D CAN to perform the spatial temporal modeling. However, 3D CAN is super computationally expensive. If we adopt a 3D CNN in both appearance branch and a motion branch, it will be super computationally expensive. Then we propose another architecture called a hybrid CAN to cut out the computation overhead on the appearance branch. So like our MTTS scan, we use the average frame on the appearance branch as well as 2D CNN on the appearance branch. But we deploy the 3D CNN on the motion branch to learn temporal relationship within a certain window. And this is a comparison with the 3D CAN, hybrid CAN, TS CAN, and 2D CAN. So you can definitely see the computational difference. For example, in the hybrid CAN, there's multiple cubes in the hybrid CAN, and in the 3D CAN, there's multiple cubes in both motion branch and appearance branch. However, in the 2D CAN, TS CAN, they're both based on the 2D CNNs. And there are also some challenges when we deploy our MTTS CAN network in the real deployment, one of the main challenges while deploying the on-device deep learning models is the gap between the high-level graph optimizations and the low-level operator optimizations on some targeted platforms such as Raspberry Pi or Pixel 4 phones or any other smartphones. Unfortunately, very few hand optimization tools are designed to handle those highly customized neural network architectures, right? Even after an architecture has been hand optimized for a target device, moving architecture to a new platform or even changing the input shapes can require some extra work, to change the optimized kernels. However, recent deep learning compilers like TVM has emerged to simplify this optimization process. These compilers separate function definitions from scheduling, such as how the code should be executed. And these separations allows developers to quickly explore schedule space without rewriting a kernel to each step. So as we showed in the figure, the TVM takes our network MTTS can from TensorFlow, and it outputs a high level differentiable IR. They call relay, and auto TVM can generate some customized kernels to some target device. In this work, we extend TVM to support MTTS scan. We provide implementation of our network in the TVM, such as attention, TSM tensor shifting module to enable the on-device deployments and optimization and low-level optimizations. Okay, so here's our result compared to the state-of-art CAN or POSE or Tron ICAs. We showed significantly improvements in the pulse estimations, about 43% improvement compared to the previous state-of-art, and also 3x improvements on the signals noise ratio. And we're going to show some demos of how this MTTS can works in reality. So this is the video demo from the AFL datasets, and you can see people are moving their heads, and MTTS can and the MT hybrid can generate much better waveform compared to the previous one. And this is a pulse measurement demo from another dataset, MMSE. So you could also see the difference between the MTTS scan versus the baseline. We also evaluate our proposed network on respiration task, and we showed there's a 20% improvement compared to previous existing state-of-art CAN. And here's the demo from AFL on the respiration estimation. Moreover, since our paper is about on-device measurements, we implement our networks and previous state-of-art 2D CAN, previous 2D CAN on the TSM and test on our low-end ARM CPU, and we showed significant acceleration. One frame inference using MTTS can only take 6 milliseconds compared with TS CAN or hybrid CAN. It has even has significant inference boost. And this is also a figure compared with all the existing architectures and our proposed architectures. So the MTTS CAN outperforms all the existing architecture 2D CAN, and our proposed hybrid CAN, the 3D CAN. I would also like to talk a little bit about the future work of this remote vital sign monitoring. Currently, researchers have been pushing towards the pulse estimation, HRV estimations, respiration estimations, and atrial fibrillation estimations, and a little bit about blood oxygen and SpO2 estimations. However, there are also some vital signs haven't been really explored with a remote measurement, like using camera to measure the blood pressure, body temperature, and glucose, and hydration. So we're all very interesting to extend our current work to those new biosignals. From a technical standpoint, there are also a lot of challenges that still remains unexplored. For example, the network has some bias towards some skin tones that included in the training data. Different people with different skin tones would demonstrate different physiological signals, and we're very interested in how to use few shots adaptations to make a personalized model to do the personalized adaptation and as well as environmental adaptations. And secondly, we're very interested in investigating the multimodality physiological sensing. Modern smartphones includes not only the not only the RGB camera sensor, but also some, for example, radar sensors or infrared camera sensors. We're very interested in develop a system to leverage all those different sensor modalities to make our system more robust. And thirdly, since our data collection requires extra efforts to get ground truth signals, collecting those data are not easy. So we're very interested in the federated learning scenarios. How do we collaboratively learn and those data and create a more robust global model, and people can pull out those global model from the cloud and to have a stronger personalized model on device. And the fourth one, we're teaming up with UW Medical School to do different trials of clinical evaluations, such as ICU evaluations. How do we deploy a camera array on the ICU room and monitor their vital signs. And please check out our GitHub repos. There are two GitHub repos. The first one is IPBG Toolbox. It's based on MATLAB, and it supports various baseline methods in this field. And we also open source our MTTS scan code. Please feel free to check it out. And just a reminder, Danny and I will do a Q&A live sessions after this talk. Please feel free to ask any questions you have. Thank you.
Hi, everyone. My name is Daniel McDuff, and I'm joined by Xin Liu. Thank you very much for attending this webinar and live Q&A. So over the next 15 minutes, we're going to be answering questions submitted by the audience. And so we'll get started with that. Some of these we've answered during the text Q&A, but we might answer again to provide more details. And you can also continue to send in questions. And if we have time, we'll try to answer as many as we can. So starting off, there were several questions, like an example from Justin, who was asking about, are there accuracy differences due to things like facial hair or maybe makeup or other things that could occlude the skin, or kind of combining this with questions about what if there's motions on the face, like for instance, blinking, eye motions, talking, mouth motions. So Xin, would you like to answer that question?
Yes. So I think that's a great question. Yes, that's true. Various motion can bring different motion noise too. So however, in our methods, we leverage a tension module to automatically detect those regions that contain physiological signals. For example, your forehead or some of your skins have more physiological signals than hairs or like your clothes. So by doing the attention module on top of the convolutional layers, so we can automatically make our networks to focus on those important regions. Also, since we used average frame in our appearance bench, and we only need to compute this attention mask every 10 frame, which can save a lot of computational power. So we can apply the same attention mask to all the different motion frames, so that you can automatically offset a lot of motion noise. Daniel, so
Great.
Okay,
Thanks.
that's my answer for this question.
And there were several questions that came in related to whether skin type affects the quality or the accuracy with which we can measure physiological signals. So thank you very much for those questions. And this is a very important issue. We do see that skin types with greater melanin content, so typically darker skin types, will absorb more light and there'll be less light reflected. So this impacts the signal to noise ratio of the underlying blood volume pulse signal. It affects respiration less because for respiration, we're typically measuring changes due to motions of the body, which are less affected by the skin type. We have some published work on this topic looking at performance, and there is also work looking at performance of wearable PPG measurement by skin type as well. So there's a few different papers you can look at to see how performance is impacted. And this is an area that we continue to do research to understand how we can mitigate performance differences across different people. Xin, another question that came in is about resolution and frame rate of the camera. Do you mind saying a bit more about what limitations there might be on that?
Yeah, so those are great questions. So prior work have shown that 36 by 36 can generate a robust performance. And of course, we can use larger resolution. However, larger resolution leads to worse latency performance. For example, if you input 100 by 100 frames to the network, it will significantly increase the computational power. So what we did in our paper is we downsampled original resolution to 36 by 36. And we have shown that this resolution can lead to about 100 FPS. So I saw there some audience also ask why high frame rate is important in this application. Actually, if you use those contact sensors like an oximeter, they usually have at least 200 hertz or 100 hertz. So the ideal range of the frame rate should be 100 hertz to 256 hertz. So in our paper, we have shown that the MTTS can work around 150 FPS. So which is ideal in a lot of applications like heart rate variability. You know, there's have to be able to detect the fine peaks during the inference. So yeah, that's my answering for the question.
Thanks. And this is also related to the questions about how far from the camera this signal can be measured. And these are related because ultimately it really depends on how many pixels in your frame contain skin, because that's the region of interest that we will be measuring the blood volume pulse from. And so the further away from the camera, not only is the intensity of reflected light going to be weaker, but also there'll be less skin pixels present. Using telephoto lenses, people have actually been able to measure the pulse signal at distances up to 40 meters or even further than that with some level of accuracy. That's with a very high quality lens. But in most of our work, we focus on using webcams and simpler cameras than that. And so in those cases, we typically limit the range to maybe 1 to 2 meters maximum, just because, you know, if someone's holding a cell phone or sitting in front of a computer, then that's the sort of range that you might expect them to be at most. In many cases, they'll be even closer than that. There were a couple of questions about measuring downstream signals from these measurements. So can you measure, for instance, whether someone is in pain, or can you use these signals to capture things like emotional changes? And that may be the case to measure changes in heart rate and respiration which occur with changes in emotional state or pain. However, with just those signals, you can't measure those things directly. For instance, some people, their physiological state may change less in a given situation, even if they experience the same amount of pain. So we just need to be careful that we don't assume that, for instance, increases in heart rate or increases in respiration rate are due to one specific cause. They could be related to lots of different changes. So context is quite important for interpreting those. Xin, there were a couple of questions about comparing this work to some work from MIT looking at using Wi-Fi signals to measure heart rate and also using Eulerian video magnification. Do you want to comment on those, or would you like me to?
Yes, you can comment on this. I can add some simple comments on this too. So, in this work, we focus on leveraging some ubiquitous device around you to detect the physiological signals. A smartphone is one of the most ubiquitous devices around you, so you can actually use your phone cameras to detect your physiological signals, and that's one of the main reasons we want to make this our network to be run at least 100 FPS and also generate great performance. Daniel, okay, continue to answer that.
Yeah, that's great. And some of the techniques we use in this work could be applied to perhaps signals from other modalities like thermal imaging. But in the case, for instance, of sensing via Wi-Fi, they're using different techniques typically to recover the heart and respiration rate. And these different modalities have different trade-offs. So when measuring via Wi-Fi, they've shown you can measure through walls, for instance. Of course, you can't do that with a camera. However, the measurements from the camera are often more accurate than can be measured via motion and motions of the body captured via Wi-Fi. So there are some trade-offs here. And just to comment on the Eulerian video magnification work, that's very relevant and related. But just to distinguish this work from that, in the magnification work, the assumption is that you know perhaps the frequency of the signal you want to magnify, whereas in this case, we're actually trying to recover that underlying frequency in order to get the most accurate measurements of the underlying physiological state, including like the heart rate and the respiration. So there were also several questions on motions of the body and lighting changes in the environment. And those are good questions. Both of those cause noise in our measurement. And so our focus is on mitigating the effect of that noise and boosting the underlying physiological signal-to-noise ratio. I would say, on balance, that motion and ambient lighting changes are probably the two biggest sources of noise in camera-based measurement, at least that in the types of applications that we see currently, which include baby monitoring of people in hospitals, and also just general fitness monitoring and tracking. Xin, do you want to comment just briefly on the goals of running on device here, in particular, how multitasking helps?
Yes, so that's a great question. So first of all, running on device meaning you don't have to upload any of your data to the cloud, and this is very important for privacy concern. In terms of multitask, if you imagine if you need to do pulse and respiration estimation separately, then you have to go through the network twice, right? So then your computational time will be doubled. However, if we use multitask learning at the same time, you can significantly reduce the computational time by half. Also, we leverage effects called arrhythmia. That means the respiration and pulse share some similar information. So we leverage this physiological effect to do the multitask learning too. Dan, do you want to add anything on top of that?
So I think that's a great, that's a great summary. So basically, by sharing parameters, we can get a large improvement in the frame rate at which we can operate, rather than essentially processing every frame twice with two different networks. And I think that's the key. We don't see a large improvement in accuracy by using multitasking, but I think there's some potential for future work in that direction too. One question came from Nina about how the speed of measurement affects the outcome. So if you're referring to frame rate, which was also a question that several other people had about what is the necessary frame rate of a video, for heart rate measurement and respiration rate measurement, frame rate could be as low as 20 or 30 frames per second, and your measurements could be quite accurate. But for heart rate variability and for measuring more subtle changes in the waveform dynamics, we would typically want a higher frame rate than that, which is why we focus on efficiency in this work. For instance, most contact sensors will measure at maybe 256 hertz, and we want to try to get as close to that as possible. At the moment, our performance that we report in this work is around 150 frames per second for the core network frame rate. There were a couple of questions about whether this can be done in different settings. And one example is, could this be done on, for instance, people who are running? In that case, there would be a lot of motion of the body. So that might make the current methods not very accurate. So for instance, if the camera was mounted on a treadmill, you may get some accurate measurements, but there could be a lot of noise. So there still needs to be further validation to really characterize performance in a high motion setting, like on a treadmill. But in more stationary settings, like when someone's sitting at a computer or when they're standing still, or even if they were doing a task that required less motion, like yoga or other types of fitness activities, I think you could measure quite accurately. It's just that, for instance, rowing or running might have a lot of body motion. There were a couple of questions about additional resources. Xin, do you want to just mention the GitHub repo that we have for our current work that's available for people to in the links?
Yeah, so you can check out those links. One GitHub link is for the IFE's toolbox. This is a MATLAB script-based toolbox, and you can use this toolbox to compute the metric from those traditional singular processing methods such as POST. And you can also go to the other link. It's called MTTS10, which includes the training and the model architecture, and also our implementation of PVN to support on-the-wise computation. You can refer this link to our NeurIPS paper.
Thanks, Xin. So I think we have time for one more question. Thank you to everyone for all your questions, and we'll try to answer as many in the text chat as possible. But just to finish off with one question about hyper or multispectral imaging. So this is a very interesting area of research. So in our work, we focused a lot on using just regular RGB cameras. But if you do have the ability to augment the hardware, so for instance, if you could have a camera with additional frequency bands, we've done a little bit of work looking at multispectral imaging using 5-band cameras, in which case we can get better measurements because we have certain bands that are tuned specifically for the frequencies that have the strongest physiological signal noise to ratio. And those typically occur around the green channel. So if you have green and orange channels rather than red, instead of green and red, then you can actually get better performance. And the same would be true if you go even further from the visible range. For instance, if you went to far infrared, you start to get thermal information. So yes, definitely multi or hyperspectral cameras can offer some benefit here. But of course, they're less ubiquitous and they're more expensive. So there's a trade-off in terms of whether they could be used in certain applications. So thank you everyone for attending this webinar. The resource list has links to the slides, to the GitHub pages that Xin mentioned, and also links to our project page and to our own personal web pages. Please, please do download those resources if you'll find them useful. And once again, thank you for all the questions and engagement. We're really passionate about this area of research and would be happy to follow up with as many questions as we can.
Thank you.